Today's the notes for 8.4. We have a warm-up at the top, and then there's like even a launch, but we're going to skip over that warm-up. It's more so just using some concepts from similarity and perimeter. Same with the second warm-up here deals with you can use some special right triangles on that one. Actually, this one I might just kind of go over real quick, just so that you see an example from special right triangles, just like yesterday. So it says Alex has a team logo patch in the shape of an equilateral triangle. So here's my equilateral triangle. And if the sides of the patch are 2.5 inches long, so each of these sides are 2.5 inches, it says, what is the approximate height of the patch? So here's the height we're looking for. It's going to form a perpendicular when we draw that. We can also split this into another right triangle. This would be specifically a 30, 60, 90 triangle. So that's where those special right triangle rules will come in. So if we know that the hypotenuse is 2.5, we would know that this 2.5 is going to get cut in half. So half of 2.5 is 1.25. That's the short leg. And so the hypotenuse would have to be 1.5 root 3. That's what we saw yesterday with the rule, right? So we have 1.5 root 3 is the height. Height equals 1.25 root 3, and the units here are in inches. Everything's in inches. It does say to round your answer to the nearest hundredths. So in that case, we could grab a calculator and actually figure out what is that approximately equal to. So 1.25 square root 3, and this comes out to about 2.17 if you round to approximately the hundredths. And again, that's in inches. All right, and that's about it. So this problem could be done using Pythagorean theorem instead, or 30, 60, 90 triangle. You don't ever have to say what method you use, but just remember we've been working through our toolbox. First thing we learned was Pythagorean theorem, and then yesterday and the day before we learned 30, 60, 90 triangle. So I prefer the 30, 60, 90 special right triangle whenever it can be used. I prefer that versus using Pythagorean theorem. But if you have two sides, like here, we did know the 2.5 and we did know the short side was 1.25 because it would get divided here into two equal parts, you could have used Pythagorean theorem as well. Now, not always are they both going to be useful, but that is something to keep in mind. So that's a quick little warm-up to kind of start thinking about all the things we've been doing up until now, and we have one more thing today to help put into our toolbox to help us with finding missing side lengths of a right triangle. Okay, so this last thing here today that we're going to see more of on Monday as well says it's an introduction to trigonometric ratios. And the idea here is, without actually doing all of this because I want to make sure we get to the actual notes, it starts off with still using the special right triangle rules to help you find the missing side lengths, to like label each scenario. They're both 30, 60, 90 triangles, but they're just two different examples. And then once you do both examples kind of simultaneously, it wants you to kind of compare different ratios. Remember ratios from unit 7 where you would like take the, let's say this short side and then the hypotenuse and divide them. Or you could take the long side and the hypotenuse and divide them, and so on. And so the reason for why we're doing that is because there are these three special ratios. They're called sine, cosine, and tangent that will be helpful as we kind of look through this. So just to practice one more special right triangle, I'll fill in this top two triangles, and then we will kind of skip over all of this until we get to the back page and we'll get to the different names of these trigonometric ratios. So this first triangle gives you the hypotenuse as 10. That means you want to cut it in half to get to your short leg. Half of 10 is 5. And then multiply 5 by root 3 to get to your long leg. So whether you use the like letters to help you, like 2b, b, and b root 3, feel free to use those to help you find the missing sides. And then same thing on this one, except this time the long leg is 9 root 3. That means the short leg is 9. You just kind of take the b part of it because this whole thing is b root 3. And then the hypotenuse is 2b, so that would be 18. Okay, so we found the missing sides. And again, for numbers 2 and 3, you would find the different ratios. It wants you to like compare the side that's adjacent, that means next to, versus this opposite side, and so on. It kind of like has you looking for the relationship, and you're going to notice that between both these triangles, that ratio would be the same. And then same thing for number 4, you would kind of say in words that the ratio is the same, so that there is something that's going on there. Let's see what's so special about it. And then we have this thing on GeoGebra that can also help us kind of find the different proportions. But we're going to, again, skip over that and go to the back so that I can tell you what those trigonometric ratios are, and then we can actually practice them. So it says here, the definition says a trigonometric ratio is a ratio between two side lengths of a triangle, specifically a right triangle, cannot work on any triangle but a right triangle. The ratios remain constant between similar triangles. That's why on the front page we had 2 similar triangles there, and every time I would find the ratios there, it would be the exact same. And because these are right triangles, we already have the one angle. We just need to know that there's another set of angles that are congruent in order to get similar triangles. So remember, it does a little recap that this is back from Unit 7. Triangles are similar if and only if their corresponding side lengths are proportional and their corresponding angles are congruent. Okay, so those are the 2 parts that are always true for triangles and really just any shapes that are similar. I know we found shortcuts when we did this back in Unit 7 with AA similarity, SSS similarity, and SAS. We didn't have to kind of show both things, but that is really like the formal definition needs to have all of those things that are met. Well, there are actually 6 trigonometric ratios that exist. That means like someone decided how to find the ratio between sides of a right triangle, but we're going to only focus on 3 of them this year. Specifically, those are going to be sine, S-I-N-E, sine, and then we have the word co kind of in front of sine, so it becomes cosine. And finally, the last one is called tangent, similar to the word that you've probably heard before, like when someone goes on a tangent. And so we'll kind of show what each of these mean. All 3 of them are the only 3 we're going to cover this year. Maybe next year in Algebra 2 or Trig you will do the rest, and then in Pre-Calc and so on you would see the rest of them as well. Now, trigonometric ratios are always given in relation to an angle. We'd have to know which angle are we talking about when we want to find the sine of something, or the cosine of something, or the tangent of something. So here are the 3 different ones that we just talked about, and these are abbreviated. So whenever you want to abbreviate sine, you just kind of ignore the E part of it. Just take off the E, and it's S-I-N. I know it's easy to say sin, but please make sure you're trying to like name it as sine. That's going to be important for like math terminology. It's always called sine, and it tells us a ratio. And it gives us this little symbol. That symbol with that circle and that line through it is called theta. So we have seen it before, but just so that we know where it came from again, because it's been a while. Theta is just like a Greek letter that is used to represent an angle measure that we don't know. So it's an unknown letter. It could have been x, it could have been a variable instead, but this is commonly what's used with sine, cosine, and tangent when we don't know which angle that is. Sometimes an angle letter can be put in, so you're going to see A and B here in just a couple of seconds here, where it's referring to the actual angles in the diagram. But notice here that the word sine starts with S. I'm going to kind of circle that. And this fraction here says opposite, or it says OPP, which stands for opposite. And the bottom says HYP, which stands for hypotenuse. So the O I'm going to circle, and the H. So I'm going to start writing out at the bottom here, S-O-H. Okay, so I'm just taking the first letter of each of those 3 things there. So I have the S from the word sine, the O from the word opposite, and then the H from the word hypotenuse. And what we would do here is look at the diagram, and we're going to eventually kind of label the diagram and work through what these mean. Before we get to those, let's just go through the next 2, and then we'll come back and try these out. So the next one says the word cosine, but remember it's abbreviated, C-O-S for cosine. And I circled the C. I'm going to circle the A for the word adjacent, and the letter H for the word hypotenuse. So C, A, and H, and I'm going to write those as capital letters. C, A, and H. Okay, and finally, the last one, it stands for tangent, but again, it's abbreviated tan. The T stands for tangent, O is opposite, and A is adjacent. So this one would be T, O, A. Now, I don't know if this is actually helpful, but this is a mnemonic device that people have learned since, I learned this when I was in school, and I'm sure well before that. It stands, like if you were to read it out loud, it says SOHCAHTOA, and it's kind of a weird sounding word that might be hopefully helpful to remember so that you can keep track of, like, what does sine stand for? What does cosine stand for? What does tangent stand for? So SOHCAHTOA tells us, like, which ones are the opposite and the hypotenuse, and then adjacent with the hypotenuse, and opposite with adjacent. So you might be wondering, well, where are the opposite, adjacent, and hypotenuse? Well, hopefully you already know the hypotenuse. In every triangle, we know that the hypotenuse is always across from the right angle. But depending on which angle we're referring to, either angle A or angle B, the opposite and the adjacent side will switch, right? So if I'm looking at angle A here, I'm going to do all of these first with angle A, the top ones, and then we're going to kind of switch it to look for angle B, and I'll kind of cross it off. So for angle A here, the side that's opposite it is the one furthest away from it, so I'm going to write the word opposite, or OPP, and from the same angle A here, the side that's touching it is called the adjacent, or ADJ. And so now that I can see what each of those are, like labeled as, I'm going to come back here and work with each of these sine and cosine. But specifically, we're going to do the ones with the letter A, because that's the angle I'm working with here. So for sine of A, remember it means opposite over hypotenuse. Opposite is side CB. Okay, hypotenuse is side AB. So I'm just writing down what the sides are, CB over AB. The order of the letters doesn't matter. You could have written BC and BA. It doesn't make a difference. It's just you know which side we're referring to. Same thing on this one. If you come over to cosine of A, same angle A, but this time it's adjacent over hypotenuse, because it's like the CAH. So adjacent goes on top, that's side AC, and the hypotenuse goes on the bottom again, which is side AB again. Then we get to this last one, and we have tangent of A again, so it's opposite over adjacent. Opposite was CB, and adjacent was AC. Okay, so that was all stuff dealing with this angle A. But as soon as I go to switch it now, I'm kind of just like crossing that off, crossing this off, crossing this off, because it's about to change. Now if I look at this bottom angle, B, and I want to write everything in terms of B, I've switched sides now so that this is opposite from angle B, and this is adjacent, this side here is adjacent from angle B. So now when I fill in opposite over hypotenuse on this one, opposite is now AC, and the hypotenuse is still AB. The cosine would be adjacent over hypotenuse, so the adjacent side to this angle B is this one right here, CB over AB, still the hypotenuse. And you can see how these like switch spots. So when I want the sine of a letter, as long as I'm looking for which angle that is, and then I want to find the cosine of the other one, they will be the same. Okay? And then tangent's the one that's a little different, though. What happens for tangent is it flips it upside down. So let's see what happened here. For angle B, opposite is now AC, and the adjacent is CB. So it takes that fraction, and it's like a reciprocal, flips it upside down. Okay, so that was just all the kind of the basics that we needed. Now we're going to get to the actual like practice, and we have to keep remembering SOHCAHTOA so that you can see what does sine go with, what does cosine go with, what does tangent go with. So for the first one, for sine of angle P here, we have opposite over hypotenuse, right? So we would pick the numbers here. It helps to label it for P first. So opposite, hypotenuse, adjacent. Opposite is 10, and the adjacent is 5√5. Okay, and so I'm sorry, I took the wrong one. It wasn't 5√5. The hypotenuse, it was opposite over hypotenuse, so O over H is 15, 10 over 15. Let me write that again. And then you would reduce the fraction. It says write the answer as a fraction and as a decimal rounded to 4 places. So if I reduce this, it comes out to 2/3. And that's my final answer. It does say to also write it as a decimal rounded to 4 places. So this would be this was a repeating decimal. So 0.666, and then you could round that up to 7. Okay, so that's the idea there. We're going to do a couple more of these. For angle P, the next one still for adjacent over hypotenuse on this one. So this one would be 5√5 divided by 15 is the hypotenuse. And then we simplify again. So this, if I simplified it, 5 divided by 15 reduces to a 3 in the denominator because you're dividing each one by 5. So it comes out to square root of 5/3. That's as a reduced fraction. And if I type this into my calculator again, you get approximately 7,454. Okay, and then we have tan of P. So this one, tan means opposite over adjacent. So 10 over, and again I can write over A, 10 over 5√5 would come out to, if I simplify 10 and 5, that would give me a 2 in the numerator, and then just a square root of 5 in the denominator. But we did do this on Thursday where we have to simplify the radical. And as soon as I go to simplify it, this comes out to 2√5 over 5. This is called rationalizing, where you're going to get rid of that denominator. All right, and then we write it in a decimal form. So typing that into the calculator gives me 0.8944. Okay, and finally, the last one, I know it's a little tight. Now we're changing what angle we use. It says cosine of R. So my adjacent is now the one next to R, and my hypotenuse is still the same, but the opposite changes. So this would now be 10 over 15 because it's adjacent over hypotenuse, and then simplify the fraction. So this would be 2/3, which is the same as the first one because remember we can switch the angle and then it comes out to be the same. All right, there it is. Okay, and then we're going to try the next one. This one we won't have to do as many. Now we're going to try to find a missing side length. So it says find the value of x. You could also technically find y, but it doesn't say to, so we're not going to bother with that. Just kind of ignore that y for now. And once you have the two sides and an angle, you want to say from that angle, label the sides. This is opposite, this is hypotenuse. So be careful to always look for hypotenuse, always across from the right angle. So when I look at that, I would say sine of 44, and the reason I chose sine is because I'm dealing with O and H. So you would say which one of them has an O and then an H, and that's going to be the SO part of SOHCAHTOA. So sine of 44 equals, opposite was x, and the hypotenuse is 14. Now this is what we're trying to solve here. We want to try to find x. So we'd say I want to get rid of that 14 and multiply it on both sides. So this is where you grab a calculator. The first thing we have to do on our calculators is check the mode. So the mode is on a graphing calculator right here. If you don't have a graphing calculator, you don't have to do this step because they're usually in default mode, just degree mode. But here on a graphing calculator, you go to mode and then you come over to where it says degree and you hit enter, and then you just get out of the screen. And we type in 14. The sine button is right here, kind of in the middle of the calculator. So sine, and then you type in 44 because we're working with degrees, 44 degrees. And as soon as you hit enter, you get this answer, and I know it looks kind of odd, but this is the final answer. It says round to the nearest tenth, so you write it as 9.7 when you round that to the nearest tenth. That's actually your answer. I know it seems like it's probably not completed, but that's actually it. All right, and that's it for this one. The last one, it says write two equations that you could use to find the value of y. So even though we kind of just ignored that for a second, it says like what could you do, and then find the value of y using each of those methods. So to start with, I'm going to go ahead and just, because this video is getting a little bit longer, so I'm going to just kind of walk through which method. If this is y and this is then adjacent, one option would be to use cosine of 44, and you would do adjacent over hypotenuse, so it'd be y over 14. And then you'd solve it and you'd be able to get the answer. I'm going to just tell you what it comes out to. 10.1 roughly. When you type in 14 cosine of 44, because it's the same thing here, you try to get that y by itself. The other option is you could do Pythagorean theorem once you have two sides and you want to find the third, right? That's one more option that we could do. And finally, there's even a third method where you could find this other angle here. And we'll do more with this on Monday to see kind of how we work through that. All right, and that's pretty much it for 8.4. Try your best with the homework, of course, and I won't check it in Monday, but I'll go over it to make sure you're understanding this. And I will see you then.